Hey, welcome back to Calculus. In section 3.7, we're going to take a look at the applications of the derivative, rates of change in natural and social sciences. So you can see our objective there. It's looking pretty busy, but a lot of this information actually isn't all that new. So let me just kind of walk us through what we're going to do in this video, and then I'm going to actually kick some of it into a second video so that this doesn't get too long. But I want to tell you, really remind you about these important phrases: average rates of change and instantaneous rate of change of a function, how to compute them, and in particular, I want to look at what their units are. So it's always very important in these contexts to understand the units on the quantities that we're talking about. And then really in this video, we're going to focus on an application in physics about particles in motion, motion along a line, and in particular, the differential relationship between position, velocity, and acceleration. All right, so that's not new, but we're going to kind of delve into it a little bit deeper here in the sense that I want to be able to be very precise about which way the particle is moving. So we want to talk about how velocity dictates the direction of motion. And we also want to be able to determine when the particle is speeding up or slowing down. All right, so that's going to be our primary applications in this video. In a second video, we'll circle back through and give some applications of this stuff in other sciences. Here I've written chemistry, population biology, but we can also talk about some applications in economics, geology, social scientists, sciences, sociology, psychology. There's no end to the application of the derivative, but we're going to do this in a second video. Okay, so what we're going to focus on here mainly is just about kind of reviewing about what we mean by average rates of change and then look at some applications in physics. Okay, let's get going. So this doesn't get too long. We'll start with just a definition slide. So we already have talked about what we mean by the average rate of change of a function. The average rate of change of a function is just the change in the output over the change in the input. I took this diagram from the book. So your author is talking about the change between 2 points called f, p, and q. So he's writing m sub pq, just m for slope. But the point is the average rate of change in the function is the change in the function's output over the change in the function's input. And the units on that would always be units of output per units of input. All right. So if the output units are, say, in our velocity example, if the output units are in meters and the inputs are measured in seconds, well, then the units on the average rate of change are meters per second. Yeah. Or if the units on the output are something, I'm just going to say this, I won't write it, millimoles per liter in a chemical reaction, time is maybe measured in seconds, then the average rate of change would be millimoles per liter per second, and so on. So it's always a unit of output per unit of input. So it's very important to understand in any context what the units on the output of your function are and what the units on the input of your function are. Because if you have both of those pieces of information, then you know what the units on the rate of change are. Okay, instantaneous rate of change is just the limit of the average rate of change over smaller and smaller changes in the input variable. That is, it's the derivative. So an instantaneous rate of change is just the derivative, and it has the exact same units as the average rate of change. Meters per second, millimoles per liter, miles per hour, cells per minute, whatever your function that you're interested in. Okay, let's look more precisely at this motion along a line. When I talk about motion along a line, I realize in life, like, you don't always just move along a straight line. Like when I go jogging in Arcata in the mornings, I don't jog along a straight line. I jog all over town. I take turns and corners, but it is possible to measure something about my jog with a single number. That's all I mean by motion along a line, is I'm kind of keeping track of how something is moving with a single number. So in my jogging example, that single number could be the distance from my house. At any given moment in time, no matter what path I'm taking around town, I'm always some distance from my house. Yeah, and so I could keep track of that number. Or if I'm throwing a baseball back and forth with someone at any given moment in time, I could keep track of how high off the ground that ball is. That's a single number. So that's really all I mean by motion along a line, is that we're measuring position. We usually denote position with the function letter s, and it depends on time, and it's a single number. So you just think of it as plotting on an s number line. The value of s is this number that we're recording at time t. Okay, and then we've already talked about its velocity, the velocity of such a particle in motion. It's just the instantaneous rate of change in position with respect to time. That is, it's the derivative. The derivative of the position function with respect to time is the velocity function. And its units would be units of distance over units of time. Meters per second, miles per hour, feet per year, whatever. It depends on what you're watching. Yeah, if your function is the height of a tree or something like that, then yeah, feet per year might be reasonable units. What's acceleration? Acceleration is just the instantaneous rate of change of velocity. So it's how the velocity of the particle is changing again with respect to time. So its units are, well, units of velocity per unit of time, that is a unit of distance per unit of time squared. So signs units on acceleration are things like meters per second squared, feet per hour squared, feet per year squared, and so on. All right. Velocity has a sign on it. It can be positive or negative, and the sign of velocity indicates the direction of motion. All right. So unless we say otherwise, if our S number line is oriented horizontally, then we're going to take the positive direction of motion to be to the right. Okay. So if the velocity is positive, then the motion is to the right. If the number line is oriented vertically, then the positive direction, unless we say otherwise, is going to be up. So a positive velocity would mean that the particle was moving up. So I'll use words like that: moving right, moving left, moving up, moving down. You can always just generically say moving in the positive direction, moving in the negative direction. But the sign of the velocity tells you which one of those things you're doing. Okay, let's look at a specific example. So I took this position function from your text. It's a cubic polynomial, S of t. And let's go ahead, just for some context, say it's the motion of a particle along a line. We're measuring time in seconds. This is a typical convention that we'll just say time has to be greater than or equal to 0, even though the domain of this function is all real numbers. But we'll sort of say time starts when we hit our stopwatch greater than or equal to 0. We're measuring it in seconds. And let's say we're measuring this distance in meters. Okay, so at any given time t, S of t is a number on a number line, and I think of it as the location of a particle at time t. So for example, if I plugged in time equals 0, that polynomial evaluates out to 0. So at time 0, the position of this particle is 0 on the S number line. If we plug in a little bit later, S of 1 is 1 minus 6 plus 9. I think that's 4. So at time 1, this particle is at position 4 on this number line, and so on. So I'm just kind of interested well, you can see down here at the bottom some questions. I want to analyze the motion of this particle. Let's start by doing a differentiation calculus exercise. Let's find its velocity and acceleration, and let's include the appropriate units. So this is a perfect time for you to stop this video and calculate ahead of me, because the velocity and the acceleration are the derivatives and second derivatives, respectively, of that cubic polynomial S of t. So stop the video and compute the derivatives yourself and put in the units, and then you can start it back up and see if you get the same thing I do. So I'm looking at that polynomial S of t, and I'm going to differentiate it using the power rule. So I'm going to get 3t squared minus 12t plus 9 is the first derivative of that thing. And the units on that would be meters per second. All right. The acceleration is the derivative of velocity. So, oops, pardon me about that. Sorry about that. I'm looking at the velocity function, and I'm going to take its derivative. So I'm going to differentiate 3t squared and get 6t. Differentiate 12t and get 12. Derivative of 9 is 0. And the units on that would be meters per second squared. All right, so there's our velocity and acceleration for this particle. And I want to use that information to analyze the motion. You can see some of my questions here. I'm going to scroll. I'll have to scroll back to do some calculation. But what kind of things do I want to answer? I would like to be able to say, like, well, where's this particle stopped? Where's that particle stopped? Where is it moving right? Where is it moving left? So we said above, moving right is asking the question, where is the velocity positive? Moving left, where's the velocity negative? Where's the particle stopped? That's asking, where's the velocity equal to 0? Yeah, so I'm going to want to know where this function v is positive, negative, and 0. All right. In order to do that, I'm going to want to have a factored form of that quadratic polynomial that I've got written up there. I want to ask you about some questions that we haven't talked about. I want to know, where's this particle speeding up? Where is it slowing down? All right, so that's going to be a little bit more subtle. We'll get into it when we get down there at the bottom. But to answer any of those questions, we're going to want to know where the velocity and the acceleration are positive, negative, and zero. So we want to factor these things. I'm just going to write the answers here. You can stop the video and do the factoring at your own speed. But this velocity function, if you factor it completely, it would be 3 times the quantity t minus 1 times t minus 3. And the acceleration, I think you can see it along here with me in real time, would factor into 6 times the quantity t minus 2. All right, so I'm going to have those two factored forms of this to start answering these questions. So these questions are answered by the velocity and the acceleration and velocity together. Okay, so what am I going to do? I'm going to make something that we're going to call sign diagrams for the velocity function. So let me scroll here a little bit. You can see I've got some templates set up here. I copied our velocity function. So it's this 3 times t minus 1 times t minus 3 meters per second, and our acceleration function, 6 times t minus 2 meters per second squared. And I'm making something over here that we're going to call sign diagrams. So let me tell you what a sign diagram is. I'm suspecting you've probably seen them in a pre-calculus course, but let me remind you what they are here. So they're both number lines. They're both number lines, and on them I'm going to mark below the number line values of the input variable. Okay, so I'm marking t values down here, and then above them I'm writing the values. I've got one for velocity and one for acceleration. So let me just kind of explain here. I won't highlight so it doesn't get confusing, but let me explain what I've written here. Why did I mark t equals 1 and 3 on the velocity number line? Because t equals 1 and t equals 3 are the two numbers that make the velocity equal to 0. All right, so that's what my picture means here. When t is 1, velocity is 0. When t is 3, velocity is 0. And there are no other values of t. That's why I marked those two t values and only those two t values. All right, so stop the video and make sure that this diagram makes sense to you. I'm writing a t value below, and I'm writing what the velocity is at that t value above it. And I'm picking these strategically. This velocity function is continuous, and a continuous function cannot change from positive to negative without going through 0. So if I say took a value of t between 0 and 1, say like a half, take t equal to a half, and I plugged it into this velocity function, well, I would get 3 times 1 half minus 1 is negative, 1 half minus 3 is negative, and a positive number times a negative number times a negative number is a positive number. Okay, so what I'm going to do in my diagram here is I'm going to write some pluses above that interval from 0 to 1 because the velocity has to be positive on that entire interval. Now I'll do the same thing, testing a point. I can pick any number I like between 1 and 3. Let's pick the number 2. And what I'm doing is I'm saying, well, is v of 2 positive or negative? Okay, you can compute it exactly. You can compute what v of 2 is if you want to take a second, but I'm not really interested in v of 2. I just want to know if it's positive or negative. So thinking about t equal 2, well, 3 is positive, 2 minus 1 is positive, but 2 minus 3 is negative. And a positive times a negative is a negative result. So that means that the velocity function is negative for every value of t between 1 and 3. The intermediate value theorem guarantees that. Likewise, you can check that the velocity is positive for every value of t bigger than 3. All right, so I'm going to interpret the direction of motion from those signs. In particular, we can do it right now. Anywhere the velocity is positive, our particle is moving in the positive direction. So I'm going to write here under this that it's moving right. It's moving right there because the velocity is positive. Between time equals 1 and 3, it's moving left. After time 3, it was moving right again. All right. When is it stopped? It stopped at time t equals 1 and time t equals 3. Where should I write that? I'll write it. I'll put it over here. So our particle is stopped at t equals 1 and t equals 3. Does it make sense why I'm picking those two values? Because those are the two values where the velocity is 0, okay? So the particle is moving right for the first second, then it stops. Then it started moving left for 2 seconds until time got to 3 when it stopped again. And then it started moving right and it stays moving right for forever. Cool. Let's fill in some signs on the acceleration number line. Same kind of thing. I'm looking at this function 6 times t minus 2. And if t is less than 2, that function is negative. If t is greater than 2, that function is positive. Okay, so now what I want to do is tell you how you can use the velocity and the acceleration function together to answer the questions, where is something speeding up and where is something slowing down, all right? You can't answer those questions with velocity alone. You can't answer those with acceleration alone. You need both. So let me try to explain why. I'm going to switch colors just to make it sort of pop out a little bit here. Let me switch to something, say, like green. And I'm going to draw some vertical lines through any t values where either the velocity or the acceleration was 0. All right. So the velocity was 0 at 1 and 3. That's why I drew these two. Okay. The acceleration was 0 at 2. T equals 2. That's why I drew this one. If there were any other zeros, I would have drawn more. All right. And so now let's just focus on this time interval from t equals 0 to t equal 1. Okay. We already said that the velocity was positive. The function is moving, the particle is moving to the right, the positive velocity. What are these minus signs on the acceleration? The acceleration, remember, is the derivative of velocity, right? A is v prime. So this acceleration being negative means that that positive velocity is getting smaller. The positive velocity is getting smaller. It's getting closer to 0. So that is, its absolute value is getting smaller. Its speed is getting smaller. So if you have a positive velocity that's getting smaller, then you're slowing down. Yeah, the velocity is becoming closer to 0. So because the velocity is positive and the acceleration is negative, I know that the particle is slowing. I'm just going to write slowing right there. All right. Let's compare that to this next second from 1 to 2. All right. The acceleration is still negative. The particle stopped when t is 1, and now its velocity is negative, right? The acceleration being negative means that velocity is decreasing. So you have a negative quantity that's becoming more negative, all right? So that means that its absolute value is actually getting bigger. It's getting further away from 0. So when that happens, the particle is actually speeding up. Maybe I should write slowing down, speeding up. In the second, it's speeding up because the velocity and the acceleration are both negative. All right, a negative velocity that's decreasing, it's becoming more negative. Maybe you should stop and kind of think about that for a second. Let's look at the next second. Over time equals 2 to 3, the velocity is still negative, but now the acceleration is positive. So this negative velocity is becoming less negative, right? Because it's increasing. So its absolute value is getting smaller. So over that interval, the particle's slowing down again. Slowing down. How about from 3 to infinity? This positive velocity is increasing. Everywhere the idea that I'm using is when the derivative is positive, the function is getting bigger. So the derivative of velocity is acceleration. So when this derivative down here is positive, these positive numbers are getting bigger. That is, they're getting bigger in absolute value. So it's going to be speeding up over there. Cool. So we've analyzed the direction of motion. When's the particle stopped? The particle is stopped when t is 1 and 3. When's it moving right? It's moving right from t equals 0 to 1, and then from t equals 3 to infinity. When is it moving left? From t equals 1 to 3. When's it slowing down? Well, it was slowing down from t equals 0 to 1 and from t equals 2 to 3, speeding up from 1 to 2 and 3 to infinity. So we could write all those down in interval notation. Maybe we should do that towards the end here, right? Let's just kind of summarize a little bit, and then we're going to wrap this one up. So there's kind of a schematic picture that the book draws of this particle's motion. It's schematic in the sense that, remember, the particle is just moving along a line. We're just keeping track of where this thing is on that S number line. So this kind of illusion of two-dimensional motion is really just an illusion. It's just kind of helping us draw. But let's just kind of check it out. We said that the particle was moving right for the first second. So you can see that in this picture, yeah? From time equals 0 to 1, the particle is moving right. And then where is it at time equals 1? It's at s equals 4. We computed that above. Yeah? And then it stopped right there. It stopped when time is 1 and s is 4. It stopped and changed its direction. It started moving left. It started moving left, and it moved left until t is 3, in which case it stopped again. What is the particle's position when t is 3? We didn't compute this, but if you go back up and plug 3 into that cubic polynomial, you're going to get 0. So it's sort of back to the origin on the s number line. Yeah, and then it starts moving right, and it continues to move right indefinitely, speeding up. So this picture doesn't really show you the speeding up and slowing down. It just shows you the left and right motion. All right, cool. Here's sort of a graphical way to fill in those same sign diagrams that we did above. The author has graphed this position function, the cubic polynomial s, the velocity function, that blue parabolic curve v there, and the acceleration, the green one, the line, right? And this is consistent with what we did above algebraically. Notice that that velocity function is 0 when t is 1 and 3. That's when the particle stops. And then the sign diagrams that we wrote above, we said, well, velocity was positive from 0 to 1 and from 3 to infinity, and velocity was negative between 1 and 3, right? So that just corresponds to positive velocity moving forward. Yeah, that's happening from 1 to 0 to 1 and 3 to infinity. Negative velocities are when you're moving in the backward direction, left. So above, I wasn't using words forward and backward. I was using right and left, right? And then the other thing that we analyzed was the acceleration. And this is the kind of big takeaway, if you like. I think that you should probably put this in your notes, that if you want to know when something is speeding up or slowing down, you have to compare the signs of the velocity and the acceleration. All right. So why is this thing slowing down over the first second? It's slowing down over the first second because the velocity function is positive, but the acceleration function was negative. And when you take a positive number and you multiply it by a negative number, then you get a negative number. But compare that over the next second, when t goes from 1 to 2, the acceleration is still negative, but so is the velocity. The acceleration is still negative down here, but the velocity is still is also negative. And a negative times a negative is a positive number. So that's why we're speeding up over that next one, and so on. So these are sort of the summaries over here, that if you want to know when a particle is slowing down, you need to know when its velocity and its acceleration have opposite signs. If you want to know when it's speeding up, you need to know when its velocity and acceleration have the same sign. They're either both positive or they're both negative. Okay, so that's kind of what I wanted to do in this video. I think maybe if you want, we can write down an interval notation, because I'm going to be asking you to write these things down. So in interval notation, let's just summarize some of our work. we can use this diagram that we're looking at here. So the particle is moving right on the interval, well, from 0 to 1 second. The velocity was positive there. And between sets, we use this mathematical union operator. It means or, and it was also moving right from 3 to infinity. So that's how I would record that answer in interval notation. When is it moving left? It was moving left from 1 to 3. All right. When is it speeding up? So I'm looking at when this thing has the same signs, either both positive or both negative on velocity and acceleration. It's speeding up from 1 to 2. And then again on the interval from 3 to infinity. Yeah, so when an interval has no end, we just use that infinity sign. When is it slowing down? It was slowing down from 0 to 1. And then again from 2 to 3. And notice in all cases, I'm using open intervals because if I'm talking about something moving right or left, speeding up or slowing down, you can't do that at a point in time. So I'll never use hard brackets on answers to questions like this. Okay, so I hope this was useful, and then digest it. Tune in. We're going to take another short video here where we'll talk about applications of rates of change in various other sciences, not just physics. Thanks for listening.